Let's see if it records for us. It does. Yeah, I guess it just randomly turned off. I hate when it does that. Yeah, so basically, all of these have a certain AMU. It's not exactly 35, but it's pretty close to 35, right? So let's say it's like, I don't remember the exact, but let's say it's 35.1 or something like that. That's not really the right number for it, but they have their own AMU. Then you have 3 that have their own AMU of like 37 point, whatever. Right? So we took a ratio of these two, essentially, and what the computer did in the simulation is they took a ratio of these two, and so you ended up getting this because the ratio between 70% 35 and 30% 37, or 37. And that's why this is way closer to your AMU on this side than it is on that side, right? Because it's shifted towards this way about so the 70-30 ratio. Does that make sense on like how that number came to be? Cool. So now we're going to do some math. So let's say we don't have a fancy simulation that does it for us. But luckily, we will not be completely stuck here. So this is part of your notes here. So the top of your notes here. So it's the last page of your notes. This number right here, right? So calculate the average atomic mass of potassium using the following data. You have potassium 39 and potassium 41. These are your mass for both. So potassium 39 is 38.964 AMUs, potassium 41 is 40.962 AMUs, and you have your percent abundance on the side there, which is 93.12 and 6.88. So if we were to guess on how we would start to solve this, do we have any ideas on like any guesses of what we would do to try to start solving this? Add them together?
And divide them by, I don't know, 2.
So if you divide it by 2, you just get in the middle in between, right? And so that would be if you had a 50-50 ratio, right? Yeah.
Could you multiply 62.930 times 249?
62.930 times 240. Where'd you get those numbers? Oh, you're talking about, okay, so not this one. I'm talking about the one above it. I think you were on the right idea, though, for this one. So basically, for this one, what do we think we do for potassium? For potassium, for this one right here. So if we wanted to try to figure out the ratio between these two, how do you think we can get to it?
That's a good question.
So it's kind of like what you did right here. So you said you had 64.930, and you were going to multiply it by 249, right? So if we were going to multiply, if we're going to apply that same logic to these numbers right here, what should we do?
You would take 38.964 and you multiply it by 92.12 and divide it.
You just start with multiplying it. So there's 2 different ways you can really solve this. Both will kind of lead to the same answer. But essentially, right, so we've got I wish I had my calculation on me. So we'll say 93.12. And then, what else should we do to this? So we'll get this ratio. What should we do to the other number?
To the other number or the answer to it? What should we do to the answer you get after you multiply?
So what we get we get whatever we get down here, right? And then, what about this other number to find the other part of this? Should we do the same thing to this?
Yes.
Yeah, so we'll do the same thing here. So 40.962 times 6.88. Bring that down. So we'll get both of these numbers. I don't have them on me. Does anybody want to try to calculate those on the calculator? Give me some numbers.
$3,628.32768.
3,600. Sorry.
28.
So how much is it? 3628. Point what?
327.
7, something like that, right? So I guess we're doing sig figs. We've got 4 sig figs, so let's just say we take these numbers off. So 4 sig figs. And then what about here? This number. Who's working on it? Looks like 2 of y'all working on it.
I got 281.81.
281 point what?
82.
82. So I guess this one's in 3 sig figs, so we'll just drop this to 281. Right? So what should we do with these 2 numbers now that we got them?
Multiply and divide it? Divide them?
Divide them, right? But what should we do with them first? Not multiply. You add them together, right?
Oh,
So
why did I say both?
yeah, I think you know. Yeah, you're on the right idea now. So if we add them together, let's see if I can do the mental math here. So it would be like 9, 0, carry the 1, 9, do something like that. 39, 9.
Mm-hmm.
So and then what are we dividing this by?
100.
100, exactly. So you get a final answer of 39.09. Does that make sense based on the abundance of this? Does this number make sense, right? Because we've got 39.09 AMUs. First off, is this closer to potassium 39 or potassium 41? Okay. 39, right? And does that make sense based on the abundances?
Yes.
Yeah, exactly, because it's way more potassium 39 than 41 in real life. So, yeah, that's exactly the way we could solve this. So basically what you ended up doing here, and you'll do this sometimes a lot, especially with like, when we get further into like some of the chapters, I can't remember exactly which ones we'll get into it. But what you essentially did is, okay, we got percents. So let's say we have 93.12 AMUs, and so we're taking this out of 100%, and we have 6.88 AMUs. And then you went through and divided it at the end to get the average. So that's kind of a method you could do it. Alternatively, you could just skip this step by just like multiplying by 0.9312 or like 0.0688. Does that make sense? So you could skip it that way, but this is a completely valid way to do it. Yeah.
Why did we divide by 100?
By 100? So basically, you're dealing in percents, right? So what we did is we just took the percents, and you know how percents are usually multiplied by 100? So in order to get rid of that percent, we divide it by 100, because still technically, if we're doing the math here, and we didn't use AMUs, we're basically using percents here. So we would still have it in like 39.09% AMUs, so we're dividing by 100% to get rid of the percent. Does that make sense? So yeah, basically we're just getting rid of the percent, that's why we divide by 100. But yeah, and the cool thing about this is we figured this method out just by talking about it. And so hopefully that'll stick in a little bit better, but that's essentially how this works. Does that make sense? Do I need to clarify it? Do y'all understand? Pressing you're like thinking about it?
I'm slowly processing.
Slowly processing it? But yeah, essentially, like I said, it's the ratio, right? So you take a ratio, and so an easy way to take a ratio is, again, convert it into AMUs. If you see like a gram ratio, that's another way to do it. If you have percents, you could be like, okay, let's say I have 100 grams, and so I have 93 grams of this and 6 grams of this. So it's kind of what we did there, except with AMUs. Alright? Yeah, maybe just like, make sure to have it written down, and you can like look over it. And like I said, we've got this other practice problem that you can kind of work on to see if you can do that on your own to see where we're at from there. Okay? So now we're going to do something interesting. So, we're going to talk about the mole. We've kind of talked about moles a little bit here and there, but we haven't really talked about it. So, this is carbon. I have exactly 1 mole of carbon in this beaker right here. How many atoms of carbon do you think are in this beaker if I say 1 mole? Just give me some random guesses.
1 billion.
1 billion? I think it's actually bigger than 1 billion.
Oh. 3
Wait,
billion.
3 billion? That's bigger.
Trillion?
Bigger.
Not, you can't count.
A number you can't count, it is hard for us to count, but we can put it in scientific notation if we needed to. Yeah?
10 to the power of 23.
10 to the power of 23. So it looks like you're kind of familiar with it. So we do use 10 to the power of 23 on this one, right? It's like 6.02 times 10 to the 23rd is basically it. If you're looking, I think you're looking at the notes too, so you're kind of seeing that. So yeah, so we basically have 6.02 times 10 to the 23rd elements here, or atoms here. This is 1 mole of lead. As you notice, there is much more and is a little heavier. If you want to actually like pass these around, you can kind of tell the difference. These are both 1 mole of different elements. But as you can see, they definitely weigh a lot differently.
Oh, wow.
So if we're going to take that in mind, how many atoms of lead do we have in that other beaker? What do we think?
A lot more.
A lot more? No, it's not a lot more. You think it's the same?
I don't know. That's just a guess.
That's a good guess. That's a good guess. Why do you think it's the same?
I have no idea.
No idea? Just giving a guess?
Yep.
So, all right.
Oh, it's the same.
It's the same? You remember this?
No, I read the notes.
Oh, she read the notes. Yeah, so it's exactly the same. You've got 6.02 times 10 to the 23rd atoms of lead here. So what's important to note here is like when we're talking about moles, we're really just kind of counting. It's kind of a way for us to, so we don't have to say 6.02 times 10 to the 23rd every single time. By the way, since you're looking at the notes, we'll go ahead and mention this. So this 6.02 times 10 to the 23rd is known as Avogadro's number. It's in the notes here, so honestly I should just unpause it so y'all can see it, what I'm talking about here. So, oh, it's right there. So, it's called Avogadro's number. And so basically it represents that in every mole there is 6.02 times 10 to the 23rd particles, right? And it doesn't matter regardless of what it is. If it's atoms, you've got 1 mole of atoms, 6.02 times 10 to the 23rd atoms. If you got 1 mole of molecules, let's say you've got like 1 mole of water, for example, that's still 6.02 times 10 to the 23rd molecules. Mr. Hunt added a fun definition here. If you have 1 mole of donuts, it's 6.02 times 10 to the 23rd donuts.
And you probably have 3 moles of cobs.
And 3 moles of cobs. Oh no.
How do you spell that?
Avogadro? So it's Avogadro. Apostrophe S. You can kind of phonics it out, essentially. Avogadro. Does that make sense? Okay? So, just to kind of give you an explanation, just to kind of further this point here, this is 1 mole of sugar. As you can see, definitely a big difference here, but the reason behind that is, remember, these are just like atoms, right? So let's take a look at what sucrose looks like, which is what we use for table sugar. I know a lot of you hear glucose. Sucrose is essentially like 2 glucoses bonded together, so it's a little weird, but this is what table sugar is. It's sucrose. This is the structure of sucrose. Now, as you can see, there is a whole lot of different elements bonded together here. So that's why we have way more of this sucrose here, because there's just more to it for each separate molecule. Does that make sense on that? And then of course, these two, this is just sulfur again. This is 1 mole of sulfur, and this is 1 mole of salt here. Right? So
I have a question, Mr. Sluss. How big is that number?
how big is Avogadro's, or how big is a mole?
Yes.
So,
Why don't you write it out in non-scientific notation?
yeah, we should probably do that. So, I think you'll remember me doing this a while ago. But again, if we're talking about 6.02 times 10 to the 23rd, seems manageable here, but if we're writing this out, we've got 6, 0, 2, 0, 0, 0, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There. That's 21 zeros, 6.0, or 602. that's how big this number is. So in every mole that we're dealing with, we've got this many particles, and that's why we end up using a mole. It's Latin for like heap or pile. So if you kind of want to think about it that way, it's just this big pile of just different particles, or
Okay,
the same particles.
So let's count back every 3. Okay, so then you have thousands, millions, billions, trillions, then what's next? Quadrillions. Then what?
I know there's a V word in there.
It's like
No, isn't that
I think it's
No.
quintillion, isn't it?
It's
Quint.
Quint, that's right, quint, yeah. I forget because they use different ones each one.
All right, and then the next one, 6, is going to be, it's just like in math, whatever, it's, hex would be a good guess, but it's gonna be sex, sometimes sex counts for 6, so it's sextillion,
Mhm.
Oh.
okay? So
And then-
602 sextillion, okay? Now, just, because I need you to know how big this is, okay? I don't make much money, so I have to have a side job, okay? My side job is I make marbles, okay? And last year, a guy had actually wanted a mole of marbles, okay? I guess he lost some of his marbles. They don't, have you ever heard that expression, he lost his marbles, he went nuts? Okay, 1 centimeter in diameter marble. I gotta make a mole though, that's a lot, okay? How big of a room do I need to store that mole of marbles in?
The first floor of this building.
Okay, do you think they would all fit in the first floor of this building? No way, not even close.
Oh, the whole school building.
The whole school building, wall to wall, floor to ceiling, even fill in the courtyard, up, cafeteria, both gyms, hallways, auditorium, every nook and cranny, you think that would be enough?
No.
Based upon the way I'm saying it, no.
Yeah.
Okay? For the sake of time, I'm not just gonna keep going. If you have 1 mole of marbles, 1 centimeter in diameter, not only would they fill every room in this, in Spain Park, they fill every building in the entire state of Alabama. They not only would do that, they'd fill every building in the United States. Not only that, they would cover the entire surface of the earth to a depth, and they're floating marbles, they can even cover in the ocean, 6/10 of a mile high.
Did someone actually ask you for a mole of marbles?
No. It'd be impossible. Our fastest computers would take like up to over 1 million years to be able to count to 602 sextillion. Okay? And so, what does that mean about that number? It's just like humongous, right? So if we had 602 sextillion, this is 12 grams of carbon. There are that many atoms. There's 602 sextillion atoms of carbon in here. What does that mean about the size of an atom?
It's very, very, very.
It's very, 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 very tiny. Okay? There's too tiny to count. So we had to come up with some kind of way to be able to know how many atoms or molecules are present. A dozen, how many is in a dozen? 12. Doesn't matter what you have, a dozen eggs, a dozen rolls, a dozen people, a dozen is 12. A mole is 6.02 times 10 to the 23rd. It's just we had to have that big of a number in order to have something to work with. Okay? So atoms are very tiny. Now, how did they come up with this? What was the stage? Did you say that?
No, I haven't got to that yet. But
Okay.
so the cool thing is so do y'all remember when you were messing with the online lab? Did y'all take a look at? Did you see what carbon 12's atomic mass was? No. So it turns out that carbon 12's atomic mass is exactly 12. Yeah, and so the reason that is because they based all of the atomic mass off of that. So in the same sense, they also based this number also off of carbon 12. So basically 12 grams of carbon is exactly 1 mole of carbon. And so they used that, basically that's how they ended up coming up with this number. So just to go off of conversion sake, so again, if we're talking about this number, we kind of talked that this is the number of atoms in a molecule, right? Right? So that's kind of how we figured this out. So the next question probably on some of y'all's minds is, how do I know what was 1 mole? If I can't really count it per se, I just kind of had to measure it out. So kind of like what Mr. Hobbs mentioned, there's 12 grams of carbon in this vial here that represents that 1 mole. So what we can use for that, essentially, what am I trying to say here? So it turns out that since they set it up this way by comparing everything to carbon-12, 1 AMU is actually exactly 1 gram per mole. So that's essentially how they ended up measuring this out, because if you have 12 grams of carbon, you have 1 mole. So you have carbon as 12 grams per mole, or carbon-12 does. So all those AMUs that we keep talking about, all of those, you can think of those as grams per mole as well as just AMUs. For reference, an AMU, the size of it, I believe it's mentioned in your notes, but it's like 1 point something to the negative 24th. It's not this notes, it's the other notes. I think it's under, yeah, it's under atomic mass here. It says that 1 AMU is approximately 1.66 times 10 to the 24th gram. So again, we really don't want to use that. So an easy way if we wanted to convert to grams, and how we ended up figuring that out, is that we converted from 1 mole to 1 gram using this gram per mole conversion based on this periodic table. So that's it. So one of your practice problems in there, I put on there, basically you're given 2 moles of sugar, and you have to convert between the moles to grams and then back to molecules. So again, I gave you what's known as the molar mass of that, and the molar mass I calculated just by like adding up all the elements together for that. And so basically your goal for that one sheet is just to kind of convert between moles to grams and back to molecules. So it might be a little difficult, but remember, it's all it is. This is kind of what we did with dimensional analysis. We're just using different standards. And if you need to, take a look at your fill-in notes. I think the last page does have some useful information, or mainly just to remind you what molar mass is and what I'm talking about when I use MN. There it is. It's right there on the
C.
meter.
Hope, Mackenzie Culpepper, come
So-
to attendance desk, please. Mackenzie
With that in
Culpepper.
mind, try to attempt to do it. You can scan that online, and just make a good attempt at it. I know we didn't get through the practice because we ran out of time, but see what you can do, and then when we come back, we can kind of talk about how to do it. Perfect.
Yes, it does. Then it takes you an extra 1 minute to calculate.
Yeah, sorry.
Okay. Seemed like things went pretty well in that class.
Yeah. We just ran. I just didn't time it right.
Yeah, that's my only
I didn't time it
concern or
right.
whatever is the timing.
Yeah.
We're supposed to be testing on Friday.
I think they got it, or they got the material. I think we're just going to have to drill molar mass a little bit harder.
Well, and they have to practice the math, that's
Yeah.
gonna be the thing. And you didn't do anything about molecular mass, at all. So that's all gonna have to be done tomorrow, and they're really gonna have to watch the video, they're gonna have to do practice problems on Wednesday.
Okay.
Well, it's really, they're supposed to do the study going on Wednesday. We might. I'm gonna talk to the other teachers, we may have to push it. May have to push it over the next Wednesday.
Mm.
And do it all at the same time on Wednesday.
Yeah.
Hi, Mr. Hobbs.
How are you doing today?
I'm doing great. How are you?
I'm doing well. you're just bored this weekend and needed something to do, so you say, man, I need to go watch Michelle's video, but wait, it's not there.
No, I was just like timing my work, and I was like, well, I don't see the videos. Do we not have the
I don't
videos?
know why it's so hard for me to click the 2 periods when I'm doing that